Projectile motion is one of those concepts in physics that brings together a lot of other fundamentals for students. So they get hands-on with free fall, kinematics, vectors, a lot of the basics in force and motion. So you can do that on a tabletop, but it's a lot more fun if you do it outside. With a rocket like this and a launcher like you're about to see, it can be safe, repeatable, and actually do some pretty cool math that confirms all the projectile motion equations. You can also do some other fun stuff like build your own rockets and stuff that gets into more STEM-oriented thinking. But for now, we're just going to focus on projectile motion. Okay, so this is just a quick overview of the air-powered projectile. Let's just start on how you would actually use it. And just go over the little components that are involved. This is a pressure regulator. You can hook up a bike pump here. This prevents too much pressure going in. It's got a gauge on the front so you can actually see how high the pressure is built up in the cylinder. Also has a slide valve on here, and it says pressurize is that way and launch is that way. So when you're ready to launch, you can pull the lockout clip and launch it like that. The orange tube is what connects everything, and that connects to this quick exhaust valve and the pressure chamber. When you're ready to launch, you can stake this down to the ground and adjust your angle by loosening up these wing nuts. And the angle is built in on the side, so you don't have to use a separate protractor. There's just a pointer for you. And then that's pretty much it. It's kind of that simple. You can just pressurize your bike pump, set it to your angle, slide the rocket on, and launch. You have really repeatable launches because it's all regulated. The air all vents at once. It's very predictable since you can kind of go 3, 2, 1, launch. And the base stays super still since it's all kind of staked down into the ground, or if you can put a sandbag on top if you don't have somewhere you can stab ground stakes into it. And then the rocket itself is super light, so it's safer. The nose cone is replaceable. And then I think the last most important feature is this safety valve here. So it will go off if you over pressurize this, and it will just vent all the air inside. It's also really useful for if you need to abort a launch. You can just pull this to essentially disarm or release the pressure from the entire launcher. So that's just a little bit of an overview, and we can get into more how you use this for projectile motion and then actually get outside and start shooting. The standard opening experiment is to fire the rocket straight up and time it. If the round trip is about 5 seconds, you've got 2.5 seconds up and 2.5 seconds down. Gravity pulls about 10 meters per second squared, so your launch velocity is about 25 meters per second. Now angle the launcher at 30 degrees. Your vertical component is V0 sine of 30, which is about 12.5 meters per second, and the horizontal component is V0 cosine of 30, about 21.6 meters per second. Now if we remember that gravity is about 10 meters per second squared, we can take our vertical component of 12.5 meters per second and determine that apex happens at about 1.25 seconds, giving us a total flight time of 2.5 seconds. So now we can take our horizontal component and predict the distance based on the total flight time. In this case, it's about 54 meters. When we did this, we measured about 52 meters. That's the moment that makes physics real. The equation that you just wrote down predicted within a few meters where the rocket would land. You can also extend this in a lot of directions. You can vary the launch angle, graph the range versus the angle. Students can discover that 45 degrees maximizes the range. There's also a really cool convergence when students launch the rocket at 30 degrees and 60 degrees. Going beyond projectile motion. So we'll take this rocket and the base that we have here, what's left over, our launcher, makes for a really good platform for the design, build, test sequence. So designing a rocket, building it with materials you can find pretty much anywhere, packing tape, paper, cardstock. All of this makes for a really good platform for middle school STEM classes, informal learning situations like science camps during the summer. You can even run these as activities or competitions in high school or middle school, and maybe especially at STEM camps. Teams can compete to see who can manipulate those variables to build the best rocket and have a really good exploration of what goes into building a decent rocket. It's more complicated than it sounds. It is sort of rocket science, but it's a very nice intro to a little bit more of the engineering practices that go into all the things we see in our physical world. With a classroom bundle, groups of students can work independently. It's really important for every student to get hands-on time with something like this so that they can take turns collecting data, launching the rocket, pressurizing the system, making sure they can see where the projectile lands, going out to measure, timing vertical launches, getting the angles, all that kind of thing. So we've already gone over the launcher. I want to talk about the other components in the bundle. First off, safety glasses. No safety squints here. This is important for every student to have, no matter what part they are playing. The other things are for finding altitude. So this is a timer where you can time vertical launches. This is an altitude finder, so you can stand back a known distance and then get the rocket in the crosshairs at the apex. One of the most important measurements is distance, so we find that with the trundle wheel. This has a readout on it that shows how many times the wheel has turned. One turn is 1 meter, so you can determine how far it goes down to the centimeter. Last but not least, we have the bike pump. This is a very nice bike pump with a gauge, and it actually screws on to that valve that you saw at the beginning. So it has a really secure connection that is much better at preventing leaks, and it also is very easy to pressurize. This one has a small diameter, and so it doesn't take quite as much of the force to pressurize the launcher to higher PSIs. Everything we saw here today you can find at arborsci.com. You can also see helpful lab activities, how-to videos, and even read about some ways that Bree Barnett-Dreyfus used the APP with her class. Links to cool labs, cool blogs, and more cool stuff are in the description.